DNN trend is a performance comparison of modern state-of-the-art deep learning methods in the problem of time series trend prediction. Trend prediction can be framed in multiple ways. In this study, we refer to using a sequence of past trends in order to predict what will happen next, or more specifically, to predict what the duration and slope of the upcoming trend will be. This study mainly focuses on temporal convolutional networks, which were tested by me, Morgan, and bidirectional long short-term memory networks, which were tested by Chesney. We compared these networks to some more commonly used networks as benchmarks, and we'll give a full list of those in the next slide. So here is the full list of model architectures tested. It's a mix of recurrent models and convolutional models. We have TCNs, Bi-LSTMs, CNNs, LSTMs, MLPs, and simple RNNs. We've used 3 datasets for our testing, which are Cape Town surface air temperatures over the last 25 years, S&P 500 closing prices over a 15-year period, and, lastly, a dataset of minutely readings of a certain household's power usage. On the left is the unprocessed data, which hasn't been segmented into trend lines, just the original unmodified time series, while on the right is the dataset after all pre-processing steps, including being median filtered and converted into a sequence of trend lines. As you can probably tell, these have varying degrees of difficulty as far as making predictions goes. Air temperature has a very predictable repeating pattern, S&P 500 is more difficult, though there is a prevailing direction, and household power usage is a more volatile and difficult to predict dataset. We also tested 2 different approaches to making these predictions. A study which a large amount of this work was guided by used what we refer to here as a dual prediction approach, which is just to say that the model has been trained to predict a trend's duration and slope simultaneously. In other words, take in a sequence of trends and output the next trend's slope and duration. We also wanted to test if there was an improvement in performance if you use what we refer to here as a single prediction approach. The difference here is that with the single prediction approach, we only predict one component of the upcoming trend, so either a model will be trained to predict duration or slope, but not both. So when using a single prediction approach, you will need to use 2 DNNs to make a prediction. Now, for some background on the poster boy DNNs being tested, which are the TCN and Bi-LSTM, essentially these are DNNs packed with many innovations over the models they are based on, and they are considered state-of-the-art DNNs. They have not been applied much to trend prediction, despite being very good at time series point prediction, especially the TCN, since it was only recently put forward by Bi et al. In 2018. So, our project in short was to measure the trend prediction capabilities of TCNs and Bi-LSTMs using dual and single prediction approaches, and compare the performance to the commonly used DNNs mentioned earlier. We can summarize the aim with 2 main research questions, which are: what performance improvements, if any, do TCNs and Bi-LSTMs offer over CNNs and LSTMs, simple RNNs and MLPs, when being used to predict trends in time series data? And do 2 single prediction models offer better predictive capabilities than one model that predicts both slope and trend? Now, onto the experiment itself. We can split our project into a few steps. We of course first have data preprocessing and hyperparameter optimization. Next, we need to decide on the performance metrics and the validation method that we'll use. Lastly, we need to design our actual experiment and create the test bench. So firstly, our data preprocessing steps are shown here. I won't get into too much detail on the first 2 as they're very standard methodologies, though median filtering and piecewise linear segmentation are the more interesting preprocessing steps that we've done. Here is a visualization of what each of these steps do. This is the Cape Town air temperature dataset. On the left we have a demonstration of median filtering, which is done to reduce signal noise, and on the right is the trend line segmentation, where the series is converted into a sequence of these trend lines, which are then used as an input for the network. Hyperparameter optimization was done using a grid search, and each configuration was tested 3 times before deciding on a best configuration. This is to avoid poorly performing unrobust configurations from being selected based on getting one lucky run where they perform much better than usual. In the final experiment, each configuration was tested 10 times when recording their performance to avoid this. Now, at its core, this is a regression problem, and so the fairest metric for comparison is to use RMSE. A slight problem though is that it can be a little bit difficult to contextualize RMSE. It's fine for comparison, but it's hard to tell if a given RMSE is good or bad in a particular problem. So, for interpretability, we also looked at the direction of each prediction and applied a sort of a filter to measure how well the predictions had the direction correct. By doing this, we can look at things like directional accuracy, which are much easier to point at and say, hey, that's really good, and give us some sense of certainty that the DNN had solved the problem effectively. We also considered the time taken to train the models. So, first up is our slope RMSE results. The TCN is definitely the winner here with an average slope RMSE across all the datasets of 0.308, while the worst performance we saw here was the single prediction RNN, which had around 0.348. It's interesting to note that for the MLP, CNN, and TCN, the single prediction approaches were better than the dual prediction approach, but this wasn't the case for the recurrent models. The reason for the lower performance with the recurrent models is likely because of the dataset sizes. After segmenting the time series into trend lines, you reduce the number of inputs by quite a lot, and generally recurrent networks prefer larger datasets. Next, we have the duration RMSE, and once again, the single prediction TCN comes out on top. What's interesting in these results is that the recurrent networks make a bit of a comeback, which suggests that they might be better at predicting duration than they are at slope, though TCN, CNN, and MLP with the single prediction approach still does better. Here, we also see a massive gap between the two approaches with the MLP. The single prediction approach was the third best, while the dual prediction approach was the worst. For slope, they were much closer in performance. So for the classification metrics, this bar graph shows the performance hierarchy of each DNN when measuring their average directional accuracy in unseen data across all three datasets. As with the previous graphs, the lighter shaded bars represent single prediction approaches and the darker ones represent dual prediction approaches. Once again, the TCN is the best here, though the rest of the performance hierarchy is not quite in line with the results of the RMSE. You should take these classification metrics with a slight grain of salt because these DNNs haven't actually been trained to classify. They've been trained on regression, so one might expect better performance if we'd actually trained them on classification. But hopefully you can look at this performance and be assured that the networks performed well at that problem. Lastly, we have the train times. We only have train times for MLP and CNN and TCN, though all recurrent models had very similar speeds to the MLP and CNN. The only real outlier here was the TCN, which took almost 3 times longer to train and test the same number of models. So, if you don't have a lot of time for hyperparameter tuning and train times, then it's definitely something to take into consideration before jumping on using a TCN. It's a much more complex architecture, and that's the price you pay for it. Finally, here are the outcomes we've achieved with this project. Firstly is the creation of our test bench. This bench is publicly available on GitHub. You can find the link on the project website, and it's essentially plug and play. It's been highly abstracted, so you won't need a ton of familiarity with deep learning in order to recreate the experiments done here, and function side effects have been minimized, so as to allow for easy changes in the future to the validation method. We've actually recently changed the validation approach to walk-forward validation for furthering of this research, as well as some other changes which we'd like to use to take the project further. And besides for that, we hope to have contributed to the body of knowledge, paved the path for more thorough research on this topic, and established some guidance for people intending to implement solutions like this.